So in this section, 5.5, we're going to talk about the derivative and antiderivative rules for logarithms and exponential functions that have a base other than e. So to start off with, we're going to take a look at the rules for a general exponential function. And so when you look at these rules, a is going to represent a constant that is typically greater than 0, but just not equal to 1. So it could be 2 to the x, 3 to the x, 4 to the x, etc. And the rule, what I want to point out today is that these rules are going to look very much like our natural logs and our natural exponential function, e to the x, but it's going to have a slight variation because of the fact that the base is different. And that slight variation is going to be just an extra coefficient that enters our derivative or antiderivative rules. So for the derivative of a to the x, it's still exponential. So it's going to behave just like e to the x in that its derivative will be itself, so a to the x, but since the base is different, the constant we're going to multiply by is the natural log of a. And you need to remember or just recognize that the natural log of a is going to be just a number. So if a, the base happened to be 2, we would just multiply by the natural log of 2 to the derivative rule. Underneath, if you want to see it as applied with the chain rule, u right here represents any function of x. And so the derivative rule with the chain rule would be itself. And so our normal derivative rule will be a to the u, a natural log of a, because the base no longer is e. And then the chain rule says we just need to kind of multiply by the derivative of u at the very end. So you see two derivatives rules written there, but you really need to recognize that that is just one rule. The top one is without the chain rule, bottom one is with the chain rule. And so while we're at it, what would the antiderivative of a to the x look like? Well, it's not going to be just a to the x, because what that says is that the derivative of a to the x is just a to the x, which is not the case. When I take the derivative of a to the x, I get that natural log of a being multiplied to it like you see right here. So if the derivative multiplies by the natural log of a, and the antiderivative has to undo that, you're going to see in this rule that we're going to then divide by the natural log of a so that it cancels. So again, the derivative rule, we multiply by the natural log of a, and when you take the antiderivative, we're going to divide by the natural log of a. So let's take a look at what the derivative rules for logarithms look like. Again, where a is some constant that's positive and not equal to 1. Well, the derivative rule, again, is going to behave very similar to natural log. The derivative of natural log was 1 over x. And you're going to see the same thing here. You're going to see 1 over x. But since the base is not e, to account for that, we're going to again have that natural log of a constant within our rule. The only difference is that constant is going to be multiplied to our denominator. So the derivative of log base a is 1 over the quantity x natural log of a. And then below it, again, with the chain rule, we would take the derivative normally, which would be 1 over the inside. We would have a natural log of a in the denominator to account for the fact that the base is not e. And then chain rule says we have to multiply by the derivative of the inside. So let's take a look at a few examples of these rules applied. Okay, so find y prime. I have a linear function being multiplied to a general exponential function, so I will need the product rule. So the product rule says take the derivative of the first one, which is 1. Derivative of x is 1. Keep the second function the same, so 5 raised to the negative 4x plus 1. And then plus, leave the x the same, and now take the derivative of the second piece, and this is our new rule for today. And I'll do this in red. The rule says it's going to be itself, so 5 negative 4x plus 1 times the natural log of 5, because it's not an e, it's a 5, it has a different base. And then chain rule says I have to multiply by the derivative of the exponent, which is negative 4. And that whole thing is our derivative. For a logarithm, the rule says, so just like natural log, it'll be 1 over the inside, so 1 over x cubed plus 2x. Since it's not a natural log, it's a base 4, I account for that by multiplying by the natural log of 4 in the denominator. And chain rule says since you don't have x on the inside, you have a function of x, I have to multiply by the derivative of the inside, which is going to be a 3x squared plus 2. And that right there is my derivative. All right, so one application, finding the equation of a tangent line at x equals 8 for the logarithmic function, log base 3 of x plus 1. So for the equation of a line, we need a point and we need a slope. So let's start with the point. We know x is 8, so to get the y value, I'm just going to plug 8 into my function. So log base 3 of 8 plus 1, well, that's just log base 3 of 9. And we should be able to do this without a calculator. Log base 3 of 9 is asking you 3 raised to what power gives you 9. And since 3 squared equals 9, this logarithm equals 2. So the point is 8 comma 2. What's the slope? Well, we always get the slope of our tangent line through the derivative. So let's find the derivative first, and then we'll plug 8 in. So taking the derivative of this logarithm, whose base is not e, it's still going to be 1 over the inside. So 1 over x plus 1. We got to multiply by the natural log of 3, because it's not an e. And then chain rule says we do need to multiply by the derivative of the inside, but fortunately the derivative of x plus 1 is just 1. That's our derivative, and we can go ahead and find the slope by plugging in 8. And so we get 1 over 9 natural log of 3, and that's our slope. So our final answer I'll do in red here, the equation of the line in point-slope form. So the final answer is going to be y minus 2 equals our slope, 1 over 9 natural log of 3 times x minus 8. All right, so a definite integral here. So I would see a couple things. One, I note that we have an exponential function in the numerator. So that's one. And the second thing is with u substitution, we're always looking for a composition and the derivative of that composition inside my integral. And again, there's a relationship between taking the derivative of a root x and dividing by a root x. We need to remember that if u is the square root of x, which is the case here, the derivative of u, because remember this is just x to the 1/2 power, the derivative will be 1/2 x to the negative 1/2 power. Or if I rewrite it, we have 1 over 2 root x dx. And it's that over root x that I was referring to when I said you need to recognize that the derivative of a square root of x gives you division by root x. That's a pattern that's useful to see to help you recognize right away that picking u equaling the square root of x would be a good choice. So let's go ahead and substitute. So I get 2 to the u, and what do I have left? I have 1 over root x dx. So to make this rule down here equal just 1 over root x, I need to multiply both sides by 2. So there'll be an extra 2 that comes out, du. And I'm going to go ahead and just change my bounds right now. So if u is just the square root of x, the bottom bound will be the square root of 1, which is 1, and the top will be the square root of 4, which is 2. And now we can go ahead and take our antiderivative. So we have 2 times. The antiderivative of 2 to the u will be 2 to the u divided by the natural log of 2. And I'm going to plug in my upper and lower bounds. So my final answer, I plug in my upper bound, I get 2 times 2 squared over the natural log of 2 minus 2 times 2 to the first power over the natural log of 2. You can simplify this further if you wish, but that is going to be our final value of this definite integral. All right, so for this last example here, we're going to look at a slightly different example of our logarithmic differentiation. Again, a recap of logarithmic differentiation is just when we strategically log both sides of an equation that we're hoping to differentiate to help us take the derivative. Before, we had used it to log both sides when the equation was really a complicated either multiplication or powers or division. So just a quick example, something like this. We logged both sides. It made it implicit on the left, but what was nice is then on the right-hand side, we could then break up and simplify that with our logarithmic properties. The ones that said if you have multiplication inside of a logarithm, you could break it up with addition. If you have division, you could break it up with subtraction. Or if you have powers, like in there we have a square root, which is to the 1/2 power, you could pull powers out front of your logarithm. Now that's not what we're going to do here, but we're going to do something similar. But I want to, before we talk about logging, I want to take a look at what we have. The function is y equals x raised to the x power. And at first glance, it may look like we've dealt with this type of a function before, but in reality, we haven't. We've dealt with two different types of functions. We've dealt with power functions, and so I'll write these here just to reference. A power function is when the base is variable and the exponent is constant. So like an x squared or an x cubed or an x to the 4th. Those are power functions, and those we take our derivative with the power rule. So the derivative would just be 2x. Versus our exponential functions, which has a constant base and a variable exponent. They look very similar, but notice they are two completely different types of functions. And then these have their own separate derivative rules for exponential functions, just itself times the natural log of 2. We don't use the power function for exponentials, and we don't use the exponential rules for power functions. They both have their own. However, what I have up here, okay, this function right here is neither. It's not a power function because its exponent is variable, and it's not exponential because its base is not constant. So we actually don't have any derivative rules to deal with this. So what do? Let me clear up some space here. We are going to log both sides of this equation, and I'll show you here in just a second what that will allow us to do if we are able to log. So I'm going to log the natural log of, natural log the y, and I'm going to natural log the right side. And what's nice, what we're allowed to do now, is on the right side, I now have a logarithm that has an exponent on the inside. And our properties of logarithms say that that exponent can be pulled out front. So I have x times the natural log of x. And if you now look at what I have three, if you will, terms, natural log of y, an x, and a natural log of x. And all three of those functions, I can now take the derivative of. So let's go ahead and do that. And we're going to do it implicitly because y is no longer all by itself. So I'm going to take the derivative with respect to x still of the natural log of y. And on the right side, I'm also going to take the derivative with respect to x of x natural log of x. On the left-hand side, I'm taking the derivative of natural log of y with respect to x. So I need the chain rule. It's going to be 1 over y times y prime. On the right-hand side, everything is made up of x's, so I don't need to use the chain rule, but I do definitely need to use the product rule. So the derivative of x is 1, leave the natural log the same, plus leave the x the same. The derivative of natural log of x is 1 over x. Well, our calculus is done. I now just need to solve for y prime. So I'll multiply both sides by y, and so I get the natural log of x plus, note right here, x times 1 over x is just plus 1, and the y comes to the other side. And what did y equal? Well, y was the original function, x raised to the x power. So our final answer is going to be natural log of x plus 1 times x to the x power. And so this is a good example of how we would use logarithmic differentiation, not just to make the derivative easier, like was the case in the example I had just shown at the prior to this example, but this is a good example of how we would need to use logarithmic differentiation to simply take the derivative. There's no other way to find y prime for this function x to the x power without logarithmic differentiation.